Thank you. So welcome everybody to our free physics talk held in honor of Heinz Pagels. As Emily was mentioning, I'm a new general member. I was elected last year. It has been very exciting. And the center has really played a significant role in my professional growth since my first visit back in 2012. This week, I'm here participating in the Leveraging the Lepton Sector as a Probe for New Physics workshop. So this is a particle physics program which started this week here at the Aspen Center. And the program aims to explore novel opportunities for discovering new fundamental physics using leptons. So these are particles such as electrons, their counterparts like muons and taus, as well as neutrinos. And today we are fortunate to have with us Dr. Nick Roth from Lawrence Berkeley National Laboratory. So Nick is an accomplished Australian physicist whose research spans the fascinating intersection of particle physics and astrophysics. Nick started his academic journey at the University of Melbourne. He got 2 degrees, actually, one in law and one in physics. And then he decided to continue physics. He got a PhD from MIT. Then he continued as a researcher, as a Miller Fellow at the University of California, Berkeley, and later as a staff member at CERN, Switzerland. And recently, Nick returned to Berkeley, where he's leading an innovative research program focused on models for dark matter. And today, Nick is gonna tell us everything about the heaviest and the lightest particles of our universe.
Okay, well, let me start out by saying thank you to all of you for coming along tonight. I really appreciate you giving up your time to let me share with you a little bit of my science. So the question that I find most compelling in physics, and the one I want to talk to you about today, is to try and understand what makes up the dark matter of our universe. In particular, I wanted to share with you a revolution that's happened in the last 10 years or so, where we've been looking at the data, and what the data is starting to tell us is that maybe we're just not thinking about this problem at all correctly. And instead of thinking about dark matter as maybe a particle that's not that different to the ones we've discovered already, instead it could be something that is much, much, much lighter, or potentially much, much heavier than what we ever thought was possible. So why this is an exciting insight is as soon as you start thinking differently about what dark matter is, you have the insight that maybe you need a different type of instrument to detect that dark matter. And now that we understand that dark matter could be very different, we're thinking about these new instruments and they're starting to come online. And so I'm extremely excited that any year now we might be on the verge of discovering what dark matter is. So that's the ultimate goal of the talk today, but I want to start out and make sure that we're all on the same page about what dark matter is. And I really want to share with you why I spend all my time thinking about this, or at least some sense about the mystery of dark matter. So actually, dark matter has a long history. There was people thinking about various ideas in this direction well over 100 years ago. But I would say our modern thinking about what dark matter is actually is due to not too long ago, about 54 years, pioneering work done by Vera Rubin and Ken Ford. And what they were doing was they were actually studying our nearest neighbor in the universe, the Andromeda Galaxy, which is this beautiful galaxy I'm showing you here. So just like the Milky Way, the Andromeda Galaxy is a spiral galaxy. But one of my favorite aspects of Andromeda is because we don't live in it, we can take beautiful images like I'm showing you here. So before diving into what these scientists did, I just want to really emphasize the remarkable work that was done here, in particular by drawing attention to the scientist who led this work, which was Vera Rubin. Now, I appreciate when you're thinking about physicists, maybe Vera Rubin isn't the one that comes to mind in the same way as others like Einstein or Feynman, for example. But Vera Rubin was an amazingly pioneering scientist who really had the insight that going and making these measurements and not believing we should just guess as how they should turn out, but actually measuring it, really unlocked this problem of dark matter, as I'm about to tell you. She did an enormous amount of pioneering work that I can't do justice here, but I really encourage you to go and have a look at it. It's amazing history and all the many challenges she overcame in her career. So maybe the most seminal result that she had was studying this Andromeda Galaxy. And what were they doing in this? Well, as you would be aware, in physics, we learned an enormous amount by studying the orbits of the planets in the solar system. Just to remind you, this is roughly to scale what's happening here. We have the sun in the center, and then we have the Earth orbiting around this. And of course, really through studying these systems, I mean, firstly, as encoded in Kepler's laws, really unlocked essentially the scientific revolution that eventually led to modern physics in the modern world in many different ways. So because of the importance of this, I want to go back and just say a few words about what's happening here, because then eventually what we're going to do is apply this logic over to the Andromeda Galaxy itself. So we need to have some sense for what's going on. So as you're all aware, the reason why the Earth is moving around the Sun is because there's a force between these two objects. They're both massive, and so we know that gravity pulls between them. So two basic details I want to remind you about what's happening here. The first of these, what dominantly controls what's going on, is the fact that the Sun is very heavy. And the other aspect of gravity that's very important is how far away these two objects are. To emphasize this, we know there are other planets, you just can't see them in the picture here. For example, well, okay, I'm about to say planet, let me not get too controversial, but there is this other one called Pluto. I mean, maybe it's, I don't know what the exact definition of it is at the moment, but it's definitely something that's orbiting the Sun. And it's orbiting the Sun at about 40 times further away than the Earth is. And it turns out if you sit down and compute it, actually Pluto is moving around the Sun at about a factor of 6 slower than the Earth is. So the fact that gravity is much weaker turns into the fact that these objects move more slowly around this. And you may not have heard of this before, but just to say it's quite intuitive that gravity has more of an impact the closer you are. Of course, we know that our universe, or especially our galaxy, is full of stars, but the star that dominantly controls the motion of the Earth is the Sun. It's not all the other ones, and it's just because the Sun is the closest. So it's going to be very important how far you are away from masses. Let's take that insight and go to the Andromeda Galaxy. What Rubin and Ford were doing was they were finding individual objects in the galaxy and trying to measure how fast they were moving. Very similar to in the solar system, the reason this is a spiral galaxy is that these objects are rotating around. And so what we've learned from this is that if we find some star or object close to the center of Andromeda, then it should be moving very quickly. If we find another one that's moving slightly further away, or because we've moved around to the other side, it'll be going in the other direction. However, it's going to be moving not as fast as that closer one is because it's further away, in the same way that Pluto moves slower than the Earth. And eventually, if we find objects in the very outer edges of this galaxy, they should be moving very, very slow. Now, of course, this all presupposes that gravity in the solar system is exactly the same as the way gravity behaves on this much larger object of an entire galaxy. But people supposed that this was the case, and this is partly the reason why nobody even ever bothered to measure this. Indeed, ahead of time, people would have told you what you should see if you made this measurement is that you have things moving very quickly in the center. The direction flips as you move through the center of Andromeda. But then as you move away, eventually, their speeds tend to zero because the gravitational influence of Andromeda becomes irrelevant, just as how the Earth isn't influenced particularly by the other stars in the galaxy. So this is what everyone thought would be the case. But Vera Rubin, being an excellent scientist, didn't just assume that the theorists had everything under control and actually went and did the measurement. And this is roughly what they saw with their first measurements was shockingly, there was a huge deviation from what was predicted here. You can see that these velocities, even for objects that they found very far out at the edges of the galaxy, were still moving extremely quickly. And not only were they moving quickly, the other aspect that's very important here is you see they're not really slowing down. As I move further and further away, they're all moving at about the same speed throughout. This was a shocking realization, really to sort of hit it home. If you are really confident in the theory of gravity, sort of what you've seen here would be like the Earth orbiting around exactly nothing. Now, of course, as a physicist, it's easy to put aside the various biological catastrophes that would be associated with the sun just disappearing. And also, I mean, historically, it would have been very hard to develop the laws of gravity if we couldn't see what was in the center here. But let's say we knew the law of gravity and then we found this system. If we really believed our theory of gravity, we would have confidence that there had to be something at the center here that is pulling on the Earth. Now, it can't interact with light, or we should have seen it, but there had to be something there, or our theory of gravity is breaking. And indeed, so too it seems to be in Andromeda. There are things we can see, but you can add it up, and it is nowhere near enough mass to be pulling on these objects in order to have them going at the speeds that we see. And the other aspect is we see that we're just running out of gas at this point. There's not enough stuff, and yet these velocities are just, or the speeds are essentially constant. So there has to be a huge amount of additional matter in this object, and our modern belief is that actually there's this huge halo of dark matter that is much larger than what we can see here by by an enormous factor, which is this large sphere of dark matter that surrounds the galaxy. And in fact, we think this surrounds all galaxies, including our own Milky Way, so we are also living in this large sphere of dark matter. Of course, you can imagine that this wasn't something that people just immediately accepted. This is an amazing claim. Even though we had very precise measurements, initially people were very skeptical. However, what's happened in the 54 years since Vera Rubin's pioneering work is that we've collected evidence from all over the universe that seem to be pointing in this same direction. To start with, I was telling you about measurements at the scale of galaxies. We look at bigger scales, like the collections of all the like these objects which include many galaxies. There are these things called galaxy clusters, which is like a solar system where each planet is a galaxy. We also see evidence for dark matter. If we look at all of the structure in the universe, we again find evidence for dark matter. And even if we look at some of the earliest baby pictures we can construct of the universe in the form of the cosmic microwave background, we find very clear evidence for dark matter. Now, I don't want to spend the entire talk telling you about how all of this evidence comes through. I'll be very happy to discuss it afterwards. But just what this tells us collectively is that this dark matter exists, and not just at a qualitative level. I can tell you very specific things about this dark matter. In particular, I can tell you that all the matter we can see, so everything in this room and all the stars in the galaxy, only makes up 16% of the matter budget. And I think this is an enormously humbling fact. It tells us that for all of our understanding in science, 84% of the matter in the universe, we honestly know it's there, but we have no idea what it is. So this is why I think this is such a compelling problem to think about. And as a particle physicist, I can come to you with a solution. The answer to dark matter is it just has to be some new particle. Now, of course, this seems incredibly self-serving for me to tell you this, and also it might at first blush seem completely preposterous. I'm telling you we have a disagreement with our measurements at the scale of galaxies, and I'm telling you I'm going to solve this problem by something at the subatomic scale. So immediately you might say, come on, that's a little bit too much. But just to remind you, when you look at these images, everything we can see with our eyes, we know to be made of particles. This is essentially the great success of the atomic hypothesis. And really the miracle of particle dark matter is that I can add a particle to the ones we know about, and there's many examples of what this could be, and I can come up with a theory that is now consistent with all of these different observations. Other ideas that have been put forward for dark matter, like for example, maybe it's actually the law of gravity that is breaking at these scales. That's an extremely interesting possibility, but so far we haven't been able to come up with a version of this that obtains consistency in the way that just adding a particle is. So, if you left at this point, that's the answer. Dark matter is just a new particle. But of course, I'm not satisfied with this. I want to know what particle and what properties does it have. Now, if you want to know anything about particles, there's actually an amazing reference called the Particle Data Group book. This is essentially an encyclopedia of particle properties, or the Wikipedia of particle physics. And if it's actually something that you can get freely available on the internet. So if you're really interested in reading all about particle properties, you can see there's a couple of pages here. You can actually order your copy and get it home. So while you're waiting for yours to arrive, let me just run you through a few highlights that you might get from reading the Particle Data Group book. In particular, I don't have my copy on my bedside table, but I can tell you at least one of my colleagues does. And he tells me that he reads several pages every day. And if you're reading through this, you might run into all sorts of remarkable coincidences. Let me point out to you my favorite that he shared with me. So there's all sorts of particles that we've discovered. One you may not have heard of, is the B meson. You may not have heard about it very much because it's a very short-lived particle, but we can do a lot of very interesting physics with it, so it's very important to physicists. And when you look up the B meson in the particle data group, I hope you can see this, but what's listed here is essentially the first entry in this thing is the mass. And it tells you that it's 5,000, roughly 280 in some units called MeV. And I'll come back to explain what I mean by these units shortly. But what my colleague pointed out to me, he's also did not grow up in the United States, and nor did I. And both of us had trouble with remembering this number 5,280 in a different context. And that is the number of feet in a mile. So if you ever have trouble remembering this fact as I do, the fact that these two numbers seem to be related, and as best I can tell, there's no reason for this, it helps me remember these two numbers that otherwise I would have no way of keeping track of, so 5,280. So that's the sort of coincidences you can run into. But of course, as you flip through this book, you'll come across other particles that you probably have heard of before. For example, the Higgs boson, which was discovered 12 years ago at CERN. And again, what you'll find if you zoom in on this you have to take my word if you can't read this, is the first entry is the Higgs mass. That has a mass of around 100 in some units of GeV, and I'll come back to that. So as defined, if you want to know what the particle of dark matter is, well, now all you need to do is keep flipping through the Particle Data Group book. It's a large book, so maybe this isn't the simplest job to do, but eventually you'll find the page on dark matter, and that will just tell you everything about it. But of course, at the moment, we don't have an entry in this particle book about dark matter because we don't know its particle properties. And indeed, when I say its particle properties, I really mean ultimately something very specific is what I want to know. And that's what's going to be this first entry in the PDG. What is the mass of this particle of dark matter? Because it's the mass that really is going to define a lot of the ways that this particle behaves, as I'll try and tease out through the rest of the talk. So this is ultimately, if I could learn one number about the universe before I leave this Earth, it would be to know what is the mass of the dark matter particle. And as I said, for a long time, we really thought we understood what this was, but there's been this revolution that's happened recently, and so that's where we're going to be going with the rest of the talk. But firstly, I want to talk a little bit about mass, because we're going to be speaking about this again and again. I want to make sure we're all on the same page about the ways that we think about mass and the different ways that we could measure it. To begin with, let me talk about mass in units you're probably familiar with, and that's the kilogram. And I'll give you three different objects. One of them is extremely light. We have the proton on the left-hand side. In the center, we have something that is extremely reasonably weighted. That would be myself. Of course, there's some fluctuations here, but that's okay. And then on the right-hand side, we have a very heavy object, and that's the sun. So if we measure in kilograms, because this is a very convenient unit for talking about things around the Earth, we find that people tend to have values that aren't too crazy. So I'm about 70 kilograms on any given day. But if we move down to something very light, it's not so easy to describe this in terms of kilograms. It turns out that I have to write it as 2 times 10 to the minus 27 kilograms. And if I go to a very heavy object like the sun, I have to go up to a value of 2 times 10 to the 30 kilograms. So just to make sure we're all on the same page here, what I'm talking about here is scientific notation. I'm sure many of you are familiar with it, but I want to make sure we're all following. So when I'm talking about this 2 times 10 to a negative power, I'm talking about how many zeros I have to insert after the decimal place before I put my value down. So by 2 by 10 to the minus 27, I'm in 0.00026 times before I put the 2 down. Very small number. On the other side, for the sun, if I have a 10 to a positive power, I'm talking about 2, and then how many zeros I have to put in before the decimal point. And so this tells me that I have an enormous number when I have 10 to a positive power and a small number when I have 10 to a negative power. However, the kilogram, as you can imagine, is not going to be particularly convenient if we're talking about particle masses. We don't want to necessarily keep track of these 10 to the minus 27s when we're talking about these. They will creep back in the rest of the talk, but at least if we want to describe the particles we're most familiar with, you can imagine maybe it makes sense to swap from, we could go from kilograms to stones, but that's actually not necessarily that helpful. We're going to need some completely different unit of mass if we want to have a natural way of describing elementary particles. And it turns out that there's a unit of measurement called the electron volt. It's just a rescaled kilogram. And in those units, the proton has a mass of 1 billion electron volts, or a giga-electron volt, or a GeV. Similarly, I can measure my own mass in GeVs. This is a number you'd be quite terrified to see if you stepped on the scales. But of course, just to remind you, it's just a rescaling. I still weigh the same amount. I've just changed the measuring scale that I'm talking about here. Lastly, if I've moved to these fundamental ways of describing particle masses, you can believe that the sun is going to be an enormous number. It's now 10 to the 57, so that's 1 with 57 zeros after it before the decimal point. And you would think this is a ridiculous set of units to describe the masses of objects like the sun. And of course, to a degree it is. But actually, just to say to you, again, I'm biased as a particle physicist, but I think that this is a much more interesting way of measuring the sun than in kilograms. The reason for this is what makes up the sun was dominantly made of hydrogen. Hydrogen has a mass of essentially a proton, because hydrogen is a proton and an electron's much lighter than a proton. So what this actually tells me is roughly how many hydrogen atoms there are in the sun. Whereas I measure it in kilograms, well, the sun is not made of nicks, so it's not necessarily the most useful way of measuring this, whereas we actually learn something from this. Nonetheless, when people are talking about stars, I can tell you they rarely use units of GeV, but just to say, I do think there's something interesting in that measurement. So now we've established the basic unit that I'm going to be putting on the ruler that I'll use to define particle masses. So of course, we're all familiar with using rulers to measure length, but what I want to do here is define a ruler for measuring the mass of different particles. So generally, we'll be working in electron volts or GeV, but always throughout, I'll be putting the lighter particles to the left of the ruler and the heavier particles to the right. So let's start out by putting 2 of the particles we've already talked about on this, in the talk on the ruler. If we're talking about units of GeV, well, I told you the proton has a mass of about 1 GeV, and the recently discovered Higgs particle has a mass of around 100 GeV. So it's much heavier than the proton, so it would be up on the right-hand side of the ruler here. So that's our starting point, but actually we've discovered many particles. So we're going to need to extend this ruler pretty quickly, because actually another particle we've all heard about is the electron, and it's about 2,000 times lighter than the proton. And actually, we very quickly run into this issue that it's very hard to fit all of the particles onto the ruler if we move like 1 GeV, 2 GeV, 3 GeV. So what I've done instead is, instead of stepping along in that way, I'm going to step through in the powers of 10 that I'm moving here. So let me just walk you through what I'm showing on this ruler. So I've got 1 electron volt at this point on the ruler here, but if I move down 3 notches, I'm at 10 to the minus 3 electron volts, which is 0.001 electron volts. And as I move up each notch, I'm multiplying this by 10 if I move to the right, or dividing by 10 if I move to the left. And actually a way of writing this out is to make use of the various SI prefixes that we have. We have a milli EV, an electron volt, a kilo EV, a mega EV, a giga EV, a tera EV, and a peta EV. And actually you've probably heard of these SI prefixes before. They're used in all different areas, but one very common one is when you're talking about computer memory, we have kilobytes, megabytes, gigabytes, etc. So it's the exact same units here, but instead of talking about memory on a computer, we're talking about mass of a particle. Just to give you some context for what I'm saying here, if we converted, instead of talking about masses, we put on the same scale dollars, well, our 0 point would of course be the most natural unit of currency, which is the Australian dollar. And then if we move up here, if we're trying to think about what is the largest quantity in money that we could put on this ruler, it would be roughly the Earth's GDP. I mean, at least that's a very large number. And it turns out that in Australian dollars, that's a little bit more than $100 trillion is where the Earth's GDP is. So what you can see from this is already on the ruler, I essentially have enough flexibility to describe any quantity I'd want to in terms of a financial value. However, I'm going to need to go even further later on when we're talking about particle physics, so different particle masses. So I just wanted to give you a sense of the scale that we already have on this ruler. And I'll leave it as an exercise for you to have a guess where a dinner at Aspen fits on this scale. Good. So I told you about 3 particles we've covered so far. We have the electron, the proton, and the Higgs. But this is just a really quick run through the many particles that we've discovered in physics. There's many of them, and they come together to form this beautiful object that we call the Standard Model. And actually, as you can see, the centerpiece of this picture is the Higgs particle that was discovered 12 years ago. And many of these particles have mass, and they actually have masses all around the range here. The lightest particle here, I'll come back to mention a caveat to this, is the electron. And the heaviest particle, there's actually one particle a little bit heavier than the Higgs called the top quark, but roughly about 100 GeV is about the scale of the heaviest states. So they live in this window of masses here. Or so we thought. For a long time, it was predicted that these particles down here, called neutrinos, which Stefan, you mentioned, were thought to be exactly massless. But actually, we learned not too long ago that that's not correct. Neutrinos actually have a mass. We don't know why. It's a very big mystery. And they have extremely small masses. Their mass is about 10 million times lighter than that of the electron, and so their masses are down at this very low end, below an electron volt here. Just to say, I won't be diving into this here because I want to talk about moving on to the next discovery, but let me not leave you with the impression that this all came together very quickly. I mean, this was a heroic amount of work to put the picture that I'm telling you about here and discovering all of these states. And even in the last 11 years, there's been 2 Nobel Prizes awarded for this. Of course, famously in 2013, there was a Nobel Prize awarded for the discovery of the Higgs, but also, maybe you're not familiar, there was a Nobel Prize given in 2015 for the discovery of effectively what told us that neutrinos had to have mass. So it's been very much an active area in the last decade or so. Also, and the last point I want to make about this ruler before I start adding dark matter masses onto this is to tell you that in addition to being able to measure the different particle masses you have here, thanks to a relation that was given to us by Einstein, E equals mc squared, I can also think about this as not only measuring mass, I can also think about this as a ruler of talking about different energy scales. I just want to mention this in case it gives you some intuition for the various scales that are going on here. For example, if I'm down at this 1 electron volt, so the 0 point on our ruler, this is the energy of photons that you see with your eyes. So when you're looking at this screen, you're seeing EV scale photons, roughly is how much energy they have. So that's sort of a nominal energy that we see all around us in the world. You can ask what's sort of the highest energies that we've been able to probe as a species, well, at least in terms of detectors that we built. And this is what's been achieved at the Large Hadron Collider at CERN in Switzerland. And they've been able to reach energies of about 1 trillion electron volts, or about a TeV. So they also cover roughly the scale that I'm showing you here. That's this ruler of particle masses, but let's get back to the main theme of the talk, which is to talk about dark matter. So if dark matter is a particle, it will have a mass that just is 1 point on this ruler, and that is really the number that we want to know. But given that we don't know this number yet, it's very interesting to consider where could dark matter live on this ruler, because as we'll find out, the way that it behaves could be very different depending upon where its mass is. To begin with, the idea that has really dominated the field in terms of what dark matter could be, even shortly after these pioneering measurements by Vera Rubin and Ken Ford, was that dark matter should be something called a weakly interacting massive particle, or often shortened to be called a WIMP. And the reason it has this name here is we say that it's weakly interacting because, remember, these particles should be everywhere. We live in a halo of dark matter, and if they interacted with us very strongly, we would feel it, okay? Or we would have seen something in one of our detectors so far. So the fact that we've seen nothing tells us that these particles are weakly interacting, and we say that they're massive particles because you can see this is very much on the heavier end of particles that we've discovered so far. but it's not dramatically different to some of the heavier particles that we've found. For example, a WIMP could easily have the same mass of the proton, for example. Okay, so let's imagine that the dark matter of our universe is a WIMP. How are we going to detect it? Well, it doesn't look that different to maybe the other particles we've discovered so far. So let's take analogy with how we've discovered other particles, say in the Standard Model, and think, could we repeat this for dark matter? And indeed, the answer is essentially we could. I mentioned to you that the Higgs was discovered at the Large Hadron Collider, and the reason for this was the LHC had enough energy to produce this Higgs particle, because there's this deep relationship between energy and mass. And so similarly, if we have a dark matter particle that's not too much heavier than, say, a TeV, we would also be able to produce it at the LHC. And this is one way that we could discover it. Now, it's not immediately trivial because we know that these dark matter particles don't interact. So you produce this, or they don't interact very strongly, and it would fly out of your detector. So how could you see that nothing was produced? Well, my experimental colleagues are very clever, and they can actually measure when there's missing energy in their detector. And so one of the ways that you could search for dark matter is it's produced at the LHC, and then you have missing energy being produced from your instrument. It's a very challenging search, but it's one that's been done for many years. So far, nothing's turned up, but it could be a discovery channel for dark matter. Another way we could think of it, I told you that what we learned from these measurements of Rubin and Ford is that there's this halo of dark matter existing around every galaxy. That means that we live in a halo of dark matter, and these dark matter particles should be flying all over the place. Again, we don't notice it because they interact very weakly, but if they interact with us at all, if we build a sensitive enough instrument, what might happen is two particles could scatter, a dark matter particle and one of the ones in our detector. We build an extremely sensitive device. What you would see, it'd be like two billiard balls colliding, but you can only see one of the billiard balls. But if one of the billiard balls on your table just started moving suddenly, probably you'd first think ghosts, but maybe eventually you could think that what actually happened there was that there was a dark matter collision. And the idea here is we want to build a sensitive enough instrument to actually tease that out. Now, if you think about for this a bit, you can imagine this is going to be an amazingly challenging measurement because all sorts of other things might be able to fake. Maybe you just didn't measure the other one accurately enough. So you need to be very, very careful with this. And this has required an enormous amount of ingenuity. We have to put these tanks that we're trying to see the scattering deep underground to try and shield them from all the various backgrounds that we have on the surface. But this, again, is a very promising way of detecting dark matter. And it's one we've been pursuing for decades and haven't seen anything yet. But I remain very excited about this way of looking for dark matter. So that's the WIMP. There are other ways of looking at it, but I would say broadly, it's a very interesting idea for what dark matter could be, but we've been building detectors for decades, and so far nothing has shown up. So you can ask, is there other particles in this window of this sort of the dark matter classics where the particle masses are similar to the states we've discovered so far? And there's several others. Another one that was very popular for a while is something called a sterile neutrino. And this is, so I didn't really go into this in detail, but neutrinos are these particles that we know are produced all throughout the universe. Many of them are coming out of the sun at any second and they're passing through us. The reason, again, you don't hear about them day to day is because they're very weakly interacting. So they're not having a huge impact on things. So if you think about that for a moment, another key fact about these neutrinos is that they're electrically neutral, so they don't talk to light. So actually a neutrino starts to sound very much like an excellent dark matter candidate. It doesn't talk to us very much, and it's extremely, it does not interact with light, so we shouldn't be able to see it if there's a huge amount of it around. And actually this is plausible and was thought it might be the case for a while, but when you run through the numbers for the type of particles that neutrinos are, it turns out that they're just a little bit too light to be dark matter. That's interesting, but that just is what it is for these types of particles. So then you could say, well, maybe there exists some other neutrino we haven't detected yet, which is slightly heavier, so it just gets around this. It's still very weakly interacting, and it doesn't interact with light. That is actually an excellent dark matter candidate, and that is something that we call sterile neutrinos. Okay, so let's imagine the dark matter is made of these states. How would we be able to detect it? Well, we draw analogy again from other particles we know about. For example, if you take a neutron outside of a nucleus, it's known that it will decay into a proton, an electron, and actually a neutrino in about 14 minutes. Similarly, you can compute for these sterile neutrinos when you run through the numbers, it also can decay. Actually, it can decay to one of the regular neutrinos, which, as I said, is very hard to see, but luckily it can also decay to a photon, which we're extremely good at seeing. I mean, even our eyes can see photons, not necessarily these photons, but we know how to look for photons. So this gives us a hope that maybe we could uncover sterile neutrino dark matter by looking for them occasionally decaying to photons. So let's think through how this would actually work. So if we're staring at Andromeda, I just really like this photo, what we know is that if we zoom in on some little box here and dark matter is made of sterile neutrinos, if we had dark matter goggles and we zoomed in on this, what we would see is these sterile neutrinos particles flying all over the place. This problem will be a lot simpler if we had dark matter goggles, so we can't know about this immediately. However, the fact that one of these particles can occasionally decay into a photon actually allows us to get very weak but plausible dark matter goggles into this, because one of these is occasionally turning into a photon. It will fly to us, we could see it, and if we see regions where there's a lot of dark matter being illuminated by these photons, well, that's exactly how we might end up discovering what dark matter is made of. And to tell you, about 10 years ago, we thought that we'd done exactly that. There was some amazing work led by Ezra Bauble and her collaborators at Harvard in this paper that came out in 2014. There were several other works, but this was the first one. And what they did is they studied, remember I mentioned these galaxy clusters. These are these like solar systems of galaxies. And it turns out just as galaxies have dark matter around them, galaxy clusters exist in a huge sphere of dark matter. So they have this enormous amount of dark matter there and are potentially great candidates to go and look for some photons coming out of there associated with the decays of CERN neutrinos. So this is what they did. I don't want to go into too much detail. They're measuring the photon energy on the x-axis. You now know these units. These are kilo electron volts, or 10 to the 3 electron, or 1,000 electron volts. And essentially, this is a proxy for how many photons they saw as they moved along. The data points are here. The prediction is in red, and remarkably, there was an excess above the red when you look at this. So if you're not a physicist, you might not think this is a very impressive plot because there's not a huge disagreement between these two things here, but I can say it really set my world alight. There was a huge amount of excitement that actually what could be causing the additional photons that are coming here is exactly the decay of these stellar neutrinos. But potentially this could be the figure that discovers what dark matter is made of. So that was very possible. And of course, while we're all excited about discovering dark matter, the other aspect of scientists is that they're often very skeptical. Not only we don't just want to discover dark matter, we want to discover dark matter correctly. And so we want to make sure that when we've seen something, we're really certain that what that is a signature of truly dark matter and not something else. So there was a huge amount of work in the community to try and understand if this is a signature of dark matter, how could I cross-check it? Or alternatively, how might I be able to exclude the possibility that this is coming from dark matter? And actually, this is something that I really dove into in my own work with my amazing collaborators, Chris Dessert and Ben Safdie. And our insight was the following. So far, people have been looking for these very distant objects which have huge amounts of dark matter in them. But we said, why don't you just look closer to home? I told you that we live in this sphere of dark matter all around us. And what that means is that every time you look out into the night sky, or every time we point a telescope at some object, you have to look through some amount of dark matter in the sphere that we live in. Now, some fraction of these will be also decaying because it should also be made of these stellar neutrinos. So every observation you ever make of the universe should be faintly illuminated by that same signal. Why this is useful is because there's all sorts of observations taken around at different directions in the universe. I can add them all together and test whether I'm seeing the same line that Bauble and her collaborators told me they were seeing in the Perseus cluster. We ran exactly that analysis. This is what we were hoping to see, this illumination around the galaxy. And unfortunately, when we unblinded our analysis, we saw exactly nothing. So that told us that whatever this is causing this line, I was very disappointed also. Whatever is causing this line, it does not seem to be associated with dark matter. Now, again, I told you that scientists are skeptics, so are they just going to immediately believe things when we say this? The answer is absolutely not. There was quite an intense back and forth. I can say there was an article written about the back and forth, which was entitled that there was a brawl between the different groups. I can say we never came to blows. But ultimately, I think that the field has come to a consensus that whatever this anomaly was, unfortunately, it isn't the discovery of dark matter. But hopefully I've given you a flavor for how dark matter could have been discovered. If we had have confirmed this and more measurements had put this together, we would have eventually concluded that this is what it was. So this sort of story I've just run you through has actually happened many times in this sort of classic window for dark matter, where the dark matter mass isn't too different to the regular particle masses that we've discovered so far. We've had some hopes, but ultimately on further investigation, it doesn't seem that that's really a signal. Now, that doesn't mean we should just give up on this area. There's still some ideas that are very important that the next generation of the types of detectors I've talked about will be able to reach. But I also think it's healthy to occasionally step back and not just plow on forward and assume that you're in the right direction. And that's actually really what we've been doing as a field. Truthfully, we've been thinking, okay, so maybe dark matter is just a WIMP and it just interacts a little bit more weakly than what we've been able to test so far. And as we build the next detector, we'll finally start to see a signal. And I think that's very possible. But also, maybe we're just not thinking about this right. Maybe dark matter just isn't a particle with a mass anything comparable to the states we've thought about so far. And it's healthy to ask, what if dark matter was much lighter? What if it was much heavier? How would we be able to detect that? So this is what I want to focus on in the rest of the talk. And as we move into this broader range of dark matter masses, I want to keep two key facts about dark matter in the back of our minds, because they're really going to help us orient the different ways that dark matter behaves as we go to the very light and the very heavy end. Firstly, if you remember when we were talking about the motion of the Earth around the sun, one of the things I said that was really important is that the sun is very heavy. Its gravity is an interaction between masses, so the sun needed to have this large mass in order to pull on the Earth. Similarly, we know that dark matter has a mass because we saw this through what Vera Rubin measured. We saw that these objects were moving faster, so there had to be this huge amount of mass within the Andromeda galaxy in order to make this correct. We don't know the mass of the individual dark matter particle, so we could either have a huge number of light particles or very few heavy particles, and they would add up to get the same mass. So what we've measured locally is that through the motion of stars around us, we can see that roughly around the location of the Earth, there's about 1 proton mass worth of dark matter per cubic centimeter. That might not sound very impressive. There is far more than 1 proton mass worth per cubic centimeter within myself and within many things around the room. But the thing that's important about this is that this is throughout all of empty space around us in the solar system. The Earth is an enormous overdensity in terms of matter if you look at the solar system, and most of the solar system is essentially just empty space. So when we average the matter over that, the fact that I have a lot more than a proton per cubic centimeter begins to be averaged down, and eventually dark matter can play a role. And certainly when you start to integrate over or look out over the scale of a galaxy, then this dark matter can really add up. So this tells me if the dark matter has a mass of around a 1 GeV, remember that's the mass of the proton, because we've measured this amount of mass here, that tells me there's about 1 proton per cubic centimeter around us on the Earth. So they're not really common, but they're not rare. The room would be full of these dark matter particles. They're just frustratingly difficult to see. But if dark matter becomes much lighter, I'm going to need many more. And if dark matter becomes much heavier, I'm going to need far fewer in order to add up to that same amount of mass. That's key fact 1. Key fact 2 is one of the foundational aspects of quantum mechanics. I'm not going to get into that in detail in this talk, but I just want to keep track of this because it's very useful. And this is something called wave-particle duality. Something that we've learned is that every particle also behaves like a wave to a degree. And if we're going to say that every particle behaves like a wave, well, then every particle should have an associated fundamental wave-like aspect. One of the foundational aspects of a wave is its wavelength. When you're thinking about waves in the water, what really one of the defining characteristics is how far away are the various peaks that you see in this. And similarly, a particle should have some wavelength associated with it. It turns out that what we know is that this wavelength is inversely proportional to the mass. That means that if I have a much lighter particle, there's a much longer wavelength. So it's going to be the peaks are going to be much further apart if you're thinking about this in terms of water waves. Or if I have a much heavier particle, the size of the wave becomes smaller and smaller. So they go in the opposite directions to the mass. So keep those in the back of your mind. They're really going to help us orient ourselves as we move through these different mass ranges. So let's now think, what happens if dark matter becomes much lighter? So from first key fact, the particles become much more common. From the second key fact, the size of these particles or the wavelength of them becomes much larger because I'm going towards these lighter masses. So if I was thinking about dark matter particles at a GeV, I said about 1 per centimeter, and you can compute their wavelength, it's much smaller than a centimeter. So you just have a bunch of particles flying around. You can think about this as like a gas of particles, like, for example, particles in the air. But as they go lighter, the particles become more numerous and they have a much larger wavelength. Eventually, they're going to start to overlap with each other. And what happens is that you should no longer eventually think of this as a gas of particles. Instead, you should think of dark matter as some large collective wave. And this is really a remarkable insight because that tells us if we've been building instruments to look for particle scattering or to produce some particle at our colliders, well, of course, we've never seen anything because we should have instead been looking for something that behaves like some large coherent wave that is oscillating through the Earth instead of a gas of particles that occasionally one might scatter off this. Okay, so you've had this insight that your existing detectors aren't going to work, but you don't just want to give up and go home. You want to think, is there a detector I could build that could discover this type of dark matter if it's behaving like a wave oscillating through us here in the room? There's many different ways that we could detect this type of wave. But I just want to tell you about one dark matter candidate, and I'll show a couple of equations, but I'm not going to go into them in detail. Just to tell you, sort of, there's a WIMP of this wave dark matter world, sort of a particle we're most excited about, and that's something called an axion. And why axions are really interesting? Well, there's many reasons, but one reason they're very interesting is that we think they couple to electromagnetism. This is the theory that describes electric and magnetic fields and how they interact with charges. I'm just showing you Maxwell's equations here because some of you might be familiar with it, but technically the axion changes these equations here. The equations are really irrelevant for the point I want to make. Surely you can all appreciate that given the modern world around us, we're pretty good at understanding electromagnetism. It underpins essentially all technological devices that we have. And you can imagine if someone comes along and says, actually, the laws are wrong, they're slightly modified, we should be able to test this very quickly. And indeed, we know that the modification axions make should be very small, but we can predict that it actually would be so small that we might not have seen it so far. But if we look hard enough, we could detect it. So that's the basic idea. So we have this dark matter that's a wave through the Earth. It's just a wave passing everywhere, and it slightly couples to electromagnetism. How might we be able to detect this? Well, actually, there's a device that could do this that you're all familiar with, because we know how to look for essentially electromagnetic waves. We use these devices. There's one in most cars. This is a radio. Like what a radio does is it looks for electromagnetic radiation. These radio waves are passing all around us. And by tuning your radio to the right frequency, you can essentially enhance the power you pull out of that particular frequency that you're tuned into. And then by various ways of modulating that, you can pass information through this. Like, for example, what's the weather for tomorrow and all sorts of details like that. So the idea of looking for axions is that you want to build a radio that you can go from AM or FM and you swap that over to dark matter or DM to try and tune for what is the frequency of this dark matter wave. And this is how you could detect dark matter with these sorts of ideas. In many ways, I mean, some ideas about this have existed for a while, but really this is a field that's only just gotten started. And to tell you, one of the first devices or the prototypes of dark matter radio was an instrument called Abracadabra, if you can believe that's actually an acronym. But this is one of the precursors. I mean, anyway, just to prove to you this, it was a broadband resonant approach to cosmic axion detection with a B-ring apparatus. But anyway, that's a little bit ridiculous. So that instrument was sitting inside, it's actually inside this shielded region here, inside one of my colleagues' labs at MIT, which I think I correctly placed roughly on the east coast of the US here. So this is sort of a prototype device for one of these radios. And the reason we have to shield this is because there's radio waves coming from all over the place and we had to shield them out. These were actually, some of these radios were sources of backgrounds that we had to account for. There's stories about that I could tell you. But let me just show you what we saw when we collected the first data from Abracadabra, is that we saw this data here. So what I'm showing you on the x-axis is the frequency, essentially what value did I tune to look for this axion wave. And on the y-axis, I'm showing you how much power did I get out of this. And there's various ways we look for this. I can go into the specifics. But what you can see is that at certain frequencies, we saw a lot of power. And so immediately you might get excited. Is this the discovery of dark matter? Well, if you think about it for a moment more, something has to be going wrong, because I told you that dark matter could only have one frequency or one mass associated with it. But I'm seeing spikes all over the place. So I haven't detected, 100 different dark matter particles. Potentially there are other challenges. And as we zoomed into this, indeed, we found these were various background sources we hadn't excluded. We tested them one by one. It wasn't the discovery of dark matter. Again, this could give you I know, again, exactly. You have to be persistent in this game. But we learned one by one that these aren't coming from dark matter. But indeed, this could give you a flavor for what this could look like. If we were unable to exclude one of these as coming from dark matter and did more and more measurements, this is how the discovery could look like in this language here. But you can also see there's all sorts of other features here. Actually, at the low end, all of these spikes are due to vibrations. So as people were walking through neighboring rooms, there was a peak in between classes at MIT. You would get additional vibrations, and we know how to minimize those, but in the first data we had these. And then in truth, there are these large excesses at high frequencies. We have no idea where they're coming from. We know how to get rid of them. They're definitely not dark matter. We found if I cooled our electronics down, they went away, but we still don't actually know what they are. And this is just giving you a very brief insight into the messy business of actually running real experiments. It's never just you see nothing except for the signal that you're looking for. Of course, there's all sorts of other things we have to account for. However, my experimental colleagues are amazing. They're going to be able to improve on these results. And as we build these bigger versions of the radio, my hope is that we could eventually actually see a definitive signal coming out at some frequency, and that could be the discovery of dark matter. Let me give you a little bit of inject a little bit of realism into that. I think there's every chance in the coming years we'll make a discovery, but it might take a decade or two if the axion is dark matter to discover it. And the fundamental challenge is you can compute that there's roughly 20 million radio stations we have to go through. So you can imagine that's a slightly unpleasant task to slowly tune through 20 million radio stations to try and see if you actually finally find your favorite radio station. But my colleagues are optimistic they'll be able to move through this in maybe 10 to 20 years. But if we get lucky, it could be one of the first radio stations we check. So I think it's a really exciting time in these searches. But let's step back. I told you about this light dark matter and how it starts to behave like a wave, but I also cut the axis at 1/1000th of an electron volt rather randomly. Is that a fundamental limit, or could dark matter be even lighter? And the answer is it absolutely could be much, much lighter. And to understand this, we have to go back to the second key fact and remember that the wave gets larger the lighter it gets. In fact, eventually, if we made dark matter so light, the size of this object would be bigger than the observable universe. We're probably into trouble by that stage. And actually, it's not too far off, though. You go all the way down to 10 to the minus 22. That's 0.21 zeros and then a 1 electron volts. And then you run into a challenge in that this dark matter becomes bigger than some of the galaxies we've seen. Because the dark matter has to be playing a role in these galaxies, if it was much bigger than this, it wouldn't be consistent with what we've seen. So we know that dark matter has to have a mass heavier than about this. How would you discover this type of dark matter? Well, by studying these large galaxies we've seen, if we find some deviation and we stop seeing smaller and smaller structures, we actually might be finding a hint that dark matter has a mass down here. That's a very interesting way of probing this, but at the moment it's a relatively weak bound. You can see we've moved a long way from the standard model. And then as we move to the heavy end, you can ask, well, we talked about WIMPs, they were quite heavy particles, but is there some limit to how heavy dark matter could be? And again, it's going to be the second key fact that will tell us that there is a bound on how heavy particle dark matter could be. I told you that as particles get heavier, the size associated with them gets smaller. But also, I'm trying to put more and more energy or matter into this smaller and smaller space. Something going to go wrong if I try and put more and more matter into a smaller and smaller region of space? Absolutely is. Eventually, you will create a black hole. And so if dark matter becomes heavier than this 10 to the 28, that's 1 with 28 zeros and then electron volts, you can't talk about particles anymore. The fundamental object is a black hole because you've put so much mass into a tiny space. Well, then you might say to me, but then couldn't black holes be dark matter? And the answer is yes. So actually you can continue moving to the right here. There is a region where black holes could be dark matter. Ultimately, there is an upper limit on this as well. But let me just stick to the particle regime for this talk, but I'd be delighted to talk more about black hole dark matter afterwards. But if we're thinking dark matter as a particle, it could be still some fundamental particle in this enormous mass range that hasn't been probed so far. Then in my last minute or two, I just want to describe how would you search for dark matter if it was extremely heavy. Just to mention, from our first key fact, we're going to have some challenges. I told you that if dark matter has a mass of about 1 GeV, then you have about 1 particle per cubic centimeter. If the dark matter mass is way up here, then you only have 1 dark matter particle every 10,000 cubic kilometers. It's a very rare particle. And that means this detector, you're only maybe going to have 1 a year passing through it. You better capture that detector because you're going to run out of funding and stamina very quickly. Okay? So this is the challenge up at the upper end, although it's still possible. There could still be a particle passing through. The other way we talked about looking for WIMPs is completely out of the question. You would need a collider potentially bigger than the observable universe in order to get up to here. There's a lot of caveats to that statement because the LHC is only probing energies down here. This theme's completely out of reach. However, the third way that we talked about searching for classic particles, this decay of the stellar neutrinos, actually still works for these heavy dark matter candidates. It is predicted that many of these dark matter states would also be unstable and eventually decay, and you can just compute how much energy you would inject when one of these particles decayed. In fact, you can compute this through E equals mc squared. It would be the same amount of energy as when 500 kilograms of TNT is exploded. So of course, we can make bigger explosions than this, so maybe you're not impressed. But the point I want to emphasize is that this is an energy coming out of a single fundamental particle. That's an obscene amount of energy that's coming out, and it's being distributed into the various particles that come out of this and fly out throughout the universe, many of which will be protons and electrons, for example. And so that means you could easily produce protons that are flying throughout the universe with the same amount of kinetic energy as a cricket ball being bowled at a cricket match. Of course, that's the most natural way of thinking about it. You could also think about this in terms of baseballs if you prefer. So how would you think about, how would you actually go about detecting this? Well, occasionally some of these extremely energetic particles would collide with the Earth's atmosphere. It would be a slightly less dramatic event than what I'm showing you here. And what would happen is this particle would strongly interact with the particles in the atmosphere, create a shower of things that we would be able to see on the surface of the Earth if we had a sensitive enough detector. So many people have been looking for this, but what's really exciting about the moment is that we're starting to construct what will be one of the most sensitive detectors we've ever built and can hope to build in the near future to look for these types of faint signals of particles hitting the atmosphere. This is something called the Cherenkov telescope array. I'm showing you an artist's rendition of what that would look like on the right-hand side. But what's really exciting about the moment is this is not an artist's rendition. This is the first one of these telescopes that has already been constructed. And the hope is within 5 years, we'll have the whole array online and we can start look for hints that maybe the Earth is being bombarded with these extremely energetic particles. And if we work hard enough and see, we could maybe tease out that this is what dark matter is. So I think this is a very exciting time for the search for dark matter. If you press me honestly, as much as I actually work on this, and I think this is a promising way of searching for dark matter, but in my heart of hearts, I'm more excited about the possibility of still some of these classic particles or this radio search. I think these axions are extremely well motivated, and it's an extremely exciting way of looking for dark matter. But fundamentally, the universe doesn't care what's in my heart of hearts. Dark matter is what it is. And why we need to broaden our perspective is because by looking for these different possibilities, we can cover that maybe we were just too narrow in our searches and we need these broader ways of looking for dark matter in order to discover it. And if I step back again, although we don't know what the mass of dark matter is, I think we're incredibly excited as a community that we can start putting together a PDG entry for what dark matter might be. I mean, maybe adding something to the PDG isn't your aspiration in life, but I think for me, it will be a very exciting discovery. And I hope that in the coming years, myself or one of my colleagues can come back and tell you that we finally know what the dark matter mass is and all the amazing things we're learning about the universe because of that. Okay, let me leave it there. Thank you so much for all of your attention.
In my admittedly limited understanding of dark matter, dark energy, it's occurred to me that they are answers looking for questions. And I cite as an example, when radio waves were first invented, somebody invented something called the ether to explain how radio waves work. How is dark matter any different? Or when are you going to give up on particle and wave theory and go after something else?
No, that's a very fair question. And it's something we have to have the humility of. And I think to a degree we've had this recently, but maybe from your perspective, we're still relatively narrow. For a long time, we really thought that the dark matter mass, it was a whim. It was in this region here. I can go on it. We have some very good reasons for that being the case, but so far they seem to be wrong. So as a field, we've had some humility to step back and say, maybe we're not thinking about this the right way. And that's really what the point of today's talk is. But maybe we need to think about this even more generally. And to say there are members of my community who try and explore the possibility that, like, for example, gravity is modified. There's another possibility of looking at this. But to say where that idea really works is sort of at the level of these rotation curves that Vera Rubin and Ken Ford did. There you can maybe make these modified gravity works, although there's a lot of caveats to that statement as well. Some of these other ones, they just cannot seem to be explained by modified gravity. I can tell you, actually, it's the cosmic microwave background that is really the biggest problem to this. We just cannot find a way to modify gravity that is consistent with this. Now, maybe we haven't been smart enough, and I always, tell younger students that you need to keep an open mind about this. If you think you might have some way of doing this where people are open-minded about this possibility. But the other thing is, these particles, there are other reasons we might think they're there. As a particle physicist, you're not surprised to hear that. But the miracle is that these ideas really do match with all of these observational pieces of data. So I think that in the community, we are that level of open-minded, but I also think that I'm not ready to give up on the particles yet. Maybe if all of these search techniques I told you about in 20 years don't show up, usually the way that these things happen is that I will die or I will retire, and the next generation says these people were barking up the wrong tree and they go in that direction. So I hope I don't become that stubborn, but maybe this is how it will eventually go. But people do think in this direction. Thanks for the question.
Where's dark energy fit in this subject?
I mean, they have the same first word in their names and then little else, to be honest. So both of them, I mean, I think they're both fantastically provocative names. So I think it really has captured my attention. I devoted my entire life to trying to understand one of them. But fundamentally, they're doing very different things. I can say a lot more about this, but like what dark energy is doing is it's sort of pushing the universe apart. Right? We know that dark energy is behind the accelerated expansion, but what dark matter is doing is it's pulling things together more than we thought. I mean, that's a very glib answer. There's a lot more I could say about that. And people have tried to think, is there some potential ways of tying these ideas together? But at the moment, we have no fundamental way of understanding that. Or fundamental evidence that is the case. Another thing I would say is that dark matter, we have many great ideas for what it could be, maybe even too many. This is one of the challenges for actually searching for it. But I'm very optimistic the discovery of dark matter could be made within a year. I mean, it's absolutely could be one of these new experiments that comes on and discovers it. I am not as optimistic that we are going to discover what dark energy is necessarily anytime soon. It's a very, very fundamental problem where we're actually lacking good ideas, whereas that's not really the case for dark matter. It's a very interesting question, but yeah, I think that fundamentally they don't have to be related at all for the question.
No, is dark matter the same as it is?
It is not, yeah. No, thank you. No, thanks for asking that question. The reason that we, for example, know that it is not is I told you dark matter is passing through us all the time. Of course, it depends on the exact mass. If it was made of antimatter, it interacts very strongly because when antimatter and matter meet, they explode into energy. So the fact that things aren't exploding all the time is telling us that dark matter isn't made of antimatter. However, you can ask, I mean, it's not made of the antimatter of the particles we know about, but actually the antimatter of dark matter itself could play a very fundamental role. In fact, it's possible that dark matter is its own antimatter, and that when it meets itself, it explodes into energy. And so this possibility, by thinking this through carefully, actually is another way that I spend a lot of my time, that we might be able to look for these types of WIMP particles, because if their own antiparticles, when they meet each other, they'll explode into energy, and that's how we can see it. So the question of antiparticles enters very importantly into the search for dark matter, but it's not anti-hydrogen or anti-electrons, for example, that makes up dark matter.
Science, I remember hearing at one point in my young life that if there was more antimatter than matter, we wouldn't be here.
Well, that is correct, but to flip it around, we'd probably be made of antimatter and not matter, and we'd call matter antimatter. If this was exactly flipped. But again, I'm giving you a glib answer when really you're hitting at something really fundamental. Dark matter is one of the open problems that we have in physics. There is this other question about antimatter and matter are meant to be symmetric. How did they get distinguished? In the early universe, we had antimatter and matter. How did we eventually end up with just the matter around us and not the other substance? Honestly, I can't tell you. We have ideas for how that could be the case, but it's an open question in physics. And actually here there are cases where people try and explain this idea by explaining it with relation to dark matter as well. So there's many ideas pushing in this direction, but I can't guarantee you that that's actually there. So although I've given you this glib answer at the start, really the ultimate answer to the questions that you're asking, I can't tell you yet. It's something that we're thinking about in detail. It's very interesting.
It's from the back. I saw the book of all the different particles and how many there are. And then I saw the photo of the Andromeda Galaxy and how you think this dark matter is. And it's hard for me to imagine that all of that is just one type of particle, given how big the book is. What evidence do we have that all the dark matter is all one type of, whether it's a particle or a flake?
That's an extremely insightful comment. No, just to say, we don't know, honestly. However, let me give you an analogy with respect to the particles we do know of. So ultimately, in terms of to fully understand nature and all of the phenomena that we see around us are made of regular particles, we needed to discover and learn about all the particles that are made up of the standard model. However, to get most of the behavior, we really didn't need to know of these. The universe is 75% hydrogen, it's 25% helium, and of course the other aspects play a role, but they're sort of in the higher order details. So in order to understand, let's say we were dark matter and we were trying to understand regular matter, we could just assume that it's a hydrogen atom and then look for that, and then once we've made a discovery, tease more out. And so our rough expectation is that one particle will probably dominate most of what the behavior is of dark matter, but then there will be many additional particles that are in there. And this is one of the things, that the discovery of dark matter wouldn't be the end of the story. By learning more about this dark matter particle, it absolutely could be the case that there are many, many particles playing a key role in the behavior of dark matter, and this would teach us very fundamental things about the universe. But to begin with, we sort of take an Occam's razor point of view that one of them is dominating, and indeed, in the standard model, or the regular particles we know about, this isn't too far incorrect because we know hydrogen dominates what's going on. But yeah, you're absolutely right. We do believe there's more going on, but it's a good first approximation to think about this. Amazing question. Thank you.
Time for two very last questions. Disco? Yeah.
You're a dark matter physicist. I know what doctors do, what lawyers do.
Yep.
What do you do on Monday and Tuesday? What do you do between when you start your work and when you finish your day?
No, I mean, another way of rephrasing this is when the office door is closed and there's just me there, what am I actually doing, right, for example? So, of course, I mean, there's you can imagine there's all sorts of administrative things I'm doing, but in terms of the actual physics of it, I'm thinking, like, to give you some example, when this abracadabra instrument started taking some data, I showed you this earlier on, what was I doing for these experimentalists? It was actually involved in that. We have these this field called statistics, which sort of determines how likely is something that we've seen actually a discovery of a new state. I did the statistical analysis, or I was involved in the statistical analysis of this data set to actually test if there was a dark matter particle in here. Another idea that various things that you work on, for example, is let's think that dark matter is very heavy. This is something that I work on a lot. What actually would this Cherenkov telescope array see? And that's a question where you have to sit down and you have to start doing calculations. Okay, a dark matter decays, the energy is released. How many protons do I get? How many electrons do I get? How many of them have this energy, that energy? And then I need to think, how do they propagate throughout the universe? Usually these are pen and paper calculations, or, I put it on a computer occasionally to push this through. I want to give detailed predictions for the experiments to try and determine what they've seen. And then sometimes I work with the experiments to actually test, did they see dark matter or not? So there's much more to it, but this is a rough idea of honestly how I fill my days. It's quite exciting. Yeah. Thanks for the question.
Very last question.
I was just watching about the dark matter halo around the galaxy. Is the size of that consistent with the amount of mass that we expect the dark matter to have? Because I just looked on ChatGPT, which told me that the size of a galaxy is correlated with its overall mass. Or is there some bizarreness there that means that dark matter is interacting differently with gravity?
Good question. No, I mean, there's a lot to untease here. Okay, let me just go for it, even though it's at the end. Again, I have to introduce some jargon. When we're talking about units, I could convert all of this to light years, but it would slow me down. There's a unit called the parsec, which is about 3 light years, which is how we measure distance. So the Milky Way galaxy is about 30,000 parsecs, so almost 100,000 light years across. We think that the dark matter halo that it lives within has a radius or has a diameter. Sorry, the radius of the galaxy is 30,000 parsecs. The radius of the dark matter halo is 200,000 parsecs. So it's quite a bit larger. And actually, if you on Andromeda, you can see it on the sky. It's about the size of the moon. The dark matter halo would be considerably larger if we could actually see this. Then you touch on a second topic, that there seems to be this correlation between how much mass is in dark matter and how heavy the regular matter of galaxies is in the center. This is something technically called the galaxy halo connection, and it's actually one of the pieces of evidence people point to for modified gravity. However, it actually turns out that when people run simulations of how the universe formed, they find that the largest dark matter halos, they gravitate more, they pull in more regular matter, and statistically, you tend to have the more massive galaxies in the larger dark matter halos. So it's actually something that you can explain in the particle picture as well, although historically it was often put towards as modified gravity. So yeah, you're on point. There's a lot more I could say, but let me leave it there. Thanks for the question.